Now, we discussed earlier that energy can either be potential or kinetic, but sometimes an object can have both. So on your quizzes and exams, if both of them are present, you're going to need to be able to decide which one is more abundant. So I'm going to give you some examples here so that you'll be able to make that choice correctly. Okay, a stick of dynamite. Now, dynamite's an explosive, which means it has a lot of chemical potential energy. Now, suppose that stick of dynamite was thrown through the air. If someone threw a stick of dynamite across the room, it has still got its potential energy, but it also has some kinetic energy. So imagine this. If the stick of dynamite hit the wall and didn't blow up, how much damage would it do? The answer is not much. It might make a little dent in the wall. But if it hit the wall and blew up, it would blow the entire wall down. So the chemical potential energy is clearly much greater than the little bit of kinetic energy it has flying through the air. Okay, what about Usain Bolt running the 100-meter dash in the Olympics? When Usain is running, he's got a lot of kinetic energy. That's true because he's moving very fast. But where did that kinetic energy come from? The answer is it came from the chemical potential energy he had stored in his body. Imagine how many times he could run the 100-meter dash before he collapsed, exhausted, and out of fuel. Probably hundreds of times. He might have to rest in between, but he could run that same race many, many times over and over again. Each time, he could only have a certain amount of kinetic energy from his speed, but since he could do it many times, he must have many more times chemical potential energy to allow him to do that over and over again. So his potential energy clearly outweighs his kinetic energy. A rock thrown at a window, that's sort of like the stick of dynamite, except the rock really doesn't have any stored energy. It's just inert minerals. So the rock has kinetic energy. It'll certainly break the window when it hits it, but it doesn't really have any of the various types of potential energy, so this would be an example of kinetic energy. Your car driving down the freeway, sort of like the Usain Bolt example. The car has a lot of kinetic energy, clearly. If you ran into something, there would be an enormous amount of kinetic energy. But once again, where did that kinetic energy come from? And the answer is it came from the gasoline in the tank. You could pull off the side of the freeway and then accelerate back to 75 miles an hour a whole lot of times before you ran out of fuel, unless you were on fumes to start with. So you have a lot of chemical potential energy, enough to reach that 75 miles an hour of kinetic energy many times. So clearly the potential energy in the fuel tank outweighs the kinetic energy that the car has. The key thing is whether the object that's moving also has a large store of potential energy of some type in it. Rain falling from a cloud. Rain is basically just water. You know, water doesn't burn. It's got no electricity. It really doesn't have any of the normal kinds of potential energy. But in this case, it does have gravitational potential energy because it can fall all the way down from that cloud. So if the rain is up in the cloud just falling, then it's got a lot of gravitational potential because it has a long way to fall. Now the raindrop, just before it hits the ground, almost all of that gravitational potential energy has been converted into kinetic energy. So I would have to be very specific. A raindrop just before it hit the ground would be mostly kinetic energy. A raindrop just falling from the cloud, that would be mostly gravitational potential energy. Now the example I gave about Usain Bolt a few minutes ago applies to all living things. I mean, any living thing is going to have a huge amount of stored chemical potential energy. You can move around all day long if you want, and if you don't have to eat, you still have the energy to survive. People can live without food for several weeks as long as they have water because they have a lot of stored chemical potential energy. So this observation gives rise to what I like to call Phil's first law, at least first law for chapter 7, which basically says that all living things have more potential than kinetic energy. So if you're taking a quiz or exam and it's a living thing, whether it's an animal, a plant, a person, doesn't make any difference, your answer is going to be potential energy. As I said earlier, all processes involve energy. Whether it's a chemical change or a physical change, energy is always either going to be needed to make the process happen, or energy is going to be produced in the process. An exothermic process is a process that releases energy. So exothermic is like energy exiting or leaving the process. Wood burning, for example. When wood burns, there's a lot of heat given off, a lot of light. Clearly, it's an exothermic process. A ball rolling down a hill. If you roll a bowling ball down a hill and you stand at the bottom of the hill in front of it, you will immediately know it's releasing a lot of energy when it hits you. An acid-base reaction, you've done several acid-base reactions, and acid-base reactions always get nice and warm. So an acid-base reaction is going to release energy as well. And rain falling, we used that as an example a couple of minutes ago. The rain falling is going from a higher elevation to a lower elevation, so it is losing its gravitational potential energy. Basically, it's releasing that gravitational potential energy. There are also endothermic processes which require energy. So any process that takes energy in order to make it happen, that's an endothermic process. Pumping up a bicycle tire, it takes energy from you to pump that tire up. Grilling a hamburger, any kind of cooking is endothermic. Whether you use a microwave, your grill, the stove, or the oven, the job of all of those devices is to put energy into your food. So cooking is always an endothermic process. Raking leaves, they don't just rake themselves. It takes energy from you. Just like pumping that bicycle tire, you have to put energy into that rake to move those leaves into a pile. Life. Okay? Life is endothermic. Living things need energy. That's why we eat. Plants need sunlight. We eat the plants, or animals eat the plants, and we eat the animals. But living things always require a fairly consistent input of energy. If you cut that energy off, the living things will die. Wood burning, a ball rolling down a hill, an acid-base reaction, and rain falling. What do all of these exothermic processes have in common? And the answer is that once the process starts, they continue on their own. If you light a piece of wood, that wood will continue to burn on its own. If you get a ball started rolling down the hill, it will continue to roll down the hill. You don't have to keep pushing it. Gravity will make it go down the hill on its own. An acid-base reaction, once you mix that acid and base together, they are going to keep reacting because acids and bases always react. Once a raindrop falls out of a cloud, it's going to keep falling till it reaches the ground because gravity's pulling it down. Okay, how about the other four? Pumping up a bicycle tire, grilling a hamburger, raking leaves, and life. What do these endothermic processes have in common? The answer is they only continue as long as energy is added. Each of those processes needs energy, so when you stop providing the energy, the process ceases. A bicycle tire will not pump itself. As long as you keep pumping, air will go in. As soon as you stop, the process ends. If you turn off the heat on the grill, the hamburger will quit cooking. If you stop raking leaves, the leaves are just going to sit there in the yard. And of course, if we quit quit adding energy to living things, life will cease. So a process which once started continues on its own is called a spontaneous process. So spontaneous means, we usually think of spontaneous as something that simply happens on its own. But in science, the word spontaneous means that a process once begun will continue on its own. So for example, a sheet of paper is not going to light itself on fire. But if we light the sheet of paper, it will continue to burn. That makes it a spontaneous process. So a process doesn't have to start all by itself to be spontaneous. It simply has to continue on its own once we give it that little push to get it started. So my second law basically says that all spontaneous processes are exothermic. You'll notice that all four of the exothermic processes that we looked at, they all happen on their own. Once they're started, they continue. They're spontaneous. The four endothermic processes that we looked at did not occur spontaneously, as they continued as long as we pushed them by adding energy. As soon as we stopped adding energy, they stopped. So all spontaneous processes are exothermic with one little provision until chapter 15. At the end of the semester, when we get to chapter 15, we're going to find out that there is an unusual case in which an endothermic process can be spontaneous. It's pretty strange because endothermic processes are basically going uphill. We don't expect a ball to roll uphill by itself. We don't expect raindrops to go from the ground up into the clouds. But there is one kind of endothermic process that actually will happen spontaneously. So we'll talk about that later on in the semester when we get to chapter 15. Like any quantity, whether it's length, mass, or volume, measuring something like energy requires units. For energy, one of the common units that we use is the calorie. The calorie was devised about 100 years ago, and it's simply the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. Now, the calorie is not commonly used in science. The scientific unit is the joule. And the joule was developed independently of the calorie, so at some point they had to come up with a conversion between the two, and it turns out that there are just over 4 joules in a calorie. Now, the calorie that you're used to dealing with is the one that measures food calories, and that's not the same as a scientific calorie. A food calorie, which we usually represent with a capital C, equals 1,000 of our scientific calories, or we can simply refer to it as 1 kilocalorie. Now let's suppose that we wanted to use some energy to heat a pan of water. How much energy would be required to heat that water up to the boiling point? Well, the first thing we would need to know is how much water are we trying to heat. A large pan of water will take more energy than a small saucepan. The second thing we need to know is how many degrees are we trying to heat the water. If we start with cold water, we have more degrees to go to get to the boiling point than if we started with hot water. It turns out there's a third factor that also affects how much energy is required to increase the temperature of a substance, and that's called its specific heat. You can think of it as how hard is it to heat a substance. Some materials heat up very easily, some things heat up very slowly. Water happens to be very slow to heat. In the springtime and the summer, even though it's been nice and warm outside, it might be 90 degrees out, the water in your swimming pool might only be 75 degrees. It won't be very warm because water has a very high specific heat. It takes a lot of energy to heat it up. Things like metals tend to have very low specific heats. They're easy to heat up and they're quick to cool down. So the definition of specific heat is the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So it's almost the same as the definition of a calorie, except instead of using the word heating up a gram of water, we're heating up 1 gram of any substance. The specific heat of water is then very simply 1 calorie per gram degree Celsius. It takes 1 calorie to heat 1 gram of water by 1 degree. Now, as I mentioned earlier, metals tend to have very low specific heats. The specific heat of gold is only about 3/100ths of a calorie per gram degree Celsius. So it takes very little energy to heat gold up, and it takes a lot of energy to heat water. For example, if we took a pound of water and we added to that 1,000 calories of energy, the temperature would only go up by a little over 2 degrees. If we took a pound of gold and added that same 1,000 calories, the temperature would rise by a little over 73 degrees. So gold increases in temperature about 30 times faster than water.